Hi, welcome to Binance Academy's Blockchain Fundamentals course, where we will give you an introduction to blockchain technology. By the end of this course, you should know how a blockchain works at a high level, its use cases, and limitations. Let's dive in. At its core, a blockchain is a special type of database, sometimes referred to as a distributed ledger. Blockchains are one of the most common types of distributed ledger technology systems, so both terms are often used interchangeably. Keep in mind, however, that not all distributed ledger technology systems are blockchains. A blockchain stores information, just like a spreadsheet, but the information is subject to special rules. The rules are: 1. Data can be added. 2. Data cannot be removed or modified. 3. Each piece of data must point back to the previous piece. A block is a bundle of information that follows a specific format. New data can only be added to a blockchain as part of a block. So, the collection of blocks is what makes up the blockchain database. But one thing that makes blockchains unique is the fact that each block is built on top of the last one. Every individual block has a bit of information that references the block that came immediately before it. So, how are blocks connected in practice? To answer this question, we need to discuss the concept of hashing. Hashing is the process of using input data of any size to create a fixed size string, which is also called the output. And this is done through mathematical operations known as hash functions. We can use all sorts of input with variable sizes such as text, images, and videos, but the output, or the hash, will always have a predictable length. The length of the hash depends on the hashing algorithm being used. In other words, hashing consists of taking data of any size and passing it through a function that produces a fixed size hash. In blockchain systems, each block has its own hash that functions as a unique identifier, and every time a new block is created, its hash has to be produced based on the hash of the previous block. So the short answer to our question is, blocks are connected through hashes. Note that each block hash is unique because the odds of finding two pieces of data that produce the exact same hash are virtually impossible. In cryptography, we call this a hash collision. It describes the situation in which two different inputs produce the same hash as output. Therefore, being resistant to hash collisions is what prevents blockchain data from being tampered with. Why is a tamper-proof database like the blockchain useful? In a regular database, modifying or copying data is a straightforward process. However, that presents a problem. How do we store important data in a way that everyone can rely on? So far, the solution has been to trust the entities that store the data. Still, that trust can be misplaced and abused. The great benefit of blockchain is that there's no central authority that everyone needs to trust for the system to work. This means that a blockchain can act as a single source of truth in the digital world. It allows a network of users to agree on what the database contains and to synchronize any new updates. The peer-to-peer architecture of blockchains is made of a distributed network of users, each having equal rights. Updates don't need to go through a central coordinator. Every user on this network downloads blocks from others in order to create their own copy of the database. For all these reasons, we may describe blockchain as a trustless system. What are the implications of a distributed network which revolves around a single source of truth? It means security and redundancy. A blockchain can have tens of thousands of users, each storing their own copy and talking with peers. Even if many go offline, the network will continue to function. It also means immutability. Once a block is added to the blockchain, it can be considered permanent. It means trustlessness and transparency. You don't need to trust anyone. And since everyone has a copy of the blockchain, they can see and verify all of the data it holds. Next, we will review the history of blockchain technology. Who invented blockchain? The idea behind blockchain technology was described as early as 1991 by research scientists Stuart Haber and W. Scott Stornetta. The two introduced a computationally practical solution for timestamping digital documents, so that they cannot be backdated or tampered with. The system used a cryptographically secured chain of blocks to store the time-stamped documents. In 1992, Merkle trees were incorporated into the design, making it more efficient by allowing several documents to be collected into one block. However, this technology went unused and the patent lapsed in 2004, 4 years before the inception of Bitcoin. In 2004, computer scientist and cryptographic activist Hal Finney introduced a system called RPOW, or Reusable Proof of Work, to solve the so-called double spending problem. Double spending is a potential problem in a digital cash system, where a cryptocurrency or any digital asset can be copied and used more than once, like pirated movies or music. Finney's RPOW system solved this problem by keeping the ownership of tokens registered on a trusted server that was designed to allow users anywhere in the world to verify its correctness and integrity in real time. RPOW can be considered an early prototype and a significant early step in the history of cryptocurrencies. Then, in late 2008, a white paper introduced a decentralized peer-to-peer electronic cash system called Bitcoin. The white paper was posted to a cryptography mailing list by a person or group using the pseudonym Satoshi Nakamoto. Bitcoin solves the double spending problem with a decentralized peer-to-peer protocol for tracking and verifying transactions. In short, Bitcoins are mined for a reward using the proof-of-work mechanism by individual miners, and then verified by the decentralized nodes in the network. On the 3rd of January 2009, Bitcoin came to existence when the first Bitcoin block was mined by Satoshi Nakamoto, who received a reward of 50 Bitcoins. The first recipient of Bitcoin was Hal Finney. He received 10 Bitcoins from Satoshi Nakamoto in the world's first Bitcoin transaction on 12th of January 2009. Then, in 2013, Vitalik Buterin, a programmer and a co-founder of the Bitcoin magazine, stated that Bitcoin needed a scripting language for building decentralized applications. He started the development of a new blockchain-based distributed computing platform called Ethereum that featured a scripting functionality called smart contracts. Smart contracts are programs or scripts that are stored, deployed, and executed on the Ethereum blockchain. They can be used to make a transaction if certain conditions are met, for example. Developers are also able to create and publish applications that run on the Ethereum blockchain. These applications are usually referred to as decentralized applications, or dApps, and there are already many dApps running on the Ethereum blockchain. The Ethereum blockchain builds on the decentralized and distributed architecture of Bitcoin, but by introducing smart contracts, which support an ecosystem of dApps, Ethereum expands beyond Bitcoin's core functionality as a payment platform. Ethereum has also given rise to other innovations, including decentralized finance or DeFi applications. Beyond the Bitcoin and Ethereum blockchains, there have been other innovations, such as alternative consensus mechanisms to the proof-of-work mechanisms used by Bitcoin and Ethereum networks. Today, blockchain technology is gaining a lot of mainstream attention, and its application is no longer limited to cryptocurrencies. Blockchain is used in a wide range of applications and industries, including healthcare, supply chain, gaming, digital identity, governance, and energy. In the next module, we will look into how blockchain works in more detail. The interesting part of blockchain technology isn't so much the database itself, but rather how the same database can be used by a network of strangers who don't trust each other. Without a central authority, this isn't an easy task. To achieve it, blockchain networks rely heavily on a mix of game theory and cryptography. In this module, we're going to take a deeper dive into those mechanisms. It wouldn't make much sense for your bank to have a public document detailing every transaction between users. Due to their centralized client-server model, they can validate transactions in private. A blockchain, though, is a public database. Everyone needs to be able to look at a transaction and say with certainty that it's valid. If someone adds data that says, Alice gives 50,000 coins to Bob, how can we tell that Alice actually authorized the transaction? Who's to say that Bob didn't just add it himself? Maybe you could have some kind of a password system, but that gives you two options. Either you use a centralized entity to check them, or Alice publishes her password for every transaction. The former doesn't work in a decentralized setting. You might as well just use a regular database. The latter doesn't work because everyone would know Alice's password. After her first transaction, anyone can make a transaction masquerading as her. To get around this, we use some cryptography. which involves the transformation of data for the purposes of secure communication. Even if an adversary intercepts a message from Alice to Bob, they won't be able to decipher it without a special key. Something like the Vignere cipher is what we call symmetric encryption. For example, we can use the key HODL to transform our plain text into ciphertext. It's not impossible, but it'll be time-consuming for an adversary to figure out what the plain text is without knowing the key. However, if we give someone the key we use to encrypt the message, they can use it to decrypt it. That's why it's symmetric. The same key is used to encrypt and decrypt. The thing we're interested in here is public key cryptography, in which you use a pair of keys, a private key that you keep secret, and a public key that you can share. Both keys are linked, so by using your private key, you can easily generate the corresponding public key. But this only goes one way. It's virtually impossible for someone to take a public key and reverse engineer it to get the private key. Therefore, there's no security risk to you sharing the public key. In fact, you need to share it to make transactions. Private key holders can write a message and digitally sign it using their private key. By comparing a public key with a signature, you can safely assume that the person who owns the private key has written the message. This is an important building block in blockchain systems. The private key acts like a password, or rather an identity, generated mathematically. By using your private key to sign a message, you certify that you're not authorizing an action. That's why you should never share it. Anyone who knows your private key can produce a valid signature to spend your money or otherwise impersonate you. In a nutshell, blocks are made up of messages that say something like, I, Alice, pay 50,000 coins to Bob, and here is my signature to prove I authorized this transaction. That message gets passed around the peer-to-peer network as users check that the signature matches Alice's public key. If it doesn't, they'll ignore it and the transaction won't get validated. So, we figured out how to stop people from spending Alice's funds. What we haven't figured out is how to prevent Alice from spending the same funds twice. How do we decide which transaction to include in the blockchain? Who decides? How do we reach a consensus decision in a distributed system? We will answer these questions in the next module. Coordinating entities in a distributed system has been a long-standing problem in computing. Without a central coordinator calling the shots, how do you find a way to get everyone on the same page? This is the Byzantine general's problem, in which, in order to avoid catastrophic failure of a system, the system's actors must communicate with each other and agree on a single truth. Some of these actors may be unreliable. This dilemma is very applicable in computer science. Systems that can overcome the problem are said to be Byzantine fault tolerant. In blockchains, the Byzantine general's problem is mitigated by allowing all users on the network to validate the information. In the interest of precision, we'll stop referring to users as users and call them nodes instead. In the decentralized environment we're trying to create, nodes don't, or at least shouldn't, trust their peers. You never know which one could turn malicious, or whether they're unknowingly passing you false information. To combat the spread of false information, we use a blockchain to sequence the messages as they appear. If nodes want to submit a message, which in our case is a block, then they need to put in some work to prove that they're serious. This is the logic behind proof of work, a type of consensus mechanism allowing nodes to coordinate in a distributed setting. Such mechanisms ensure that all agents in the system can agree on a single truth, even if some agents fail. In proof of work, hashing is used, as we've discussed before. What we didn't mention is that there's a specific hash that nodes need to find. They hash the contents of the block they want to broadcast to the network and hope the hash matches the parameters set out by the blockchain. Remember that our block must also include the hash of the previous block, so it can only be created after the most recent one. In proof-of-work systems, it's often incredibly difficult to calculate a valid hash. Nodes use large amounts of computational power and electricity to do this. But here's the thing. Once they do find one, they send the block around the network. Anyone can easily check that it's valid and hasn't been edited, because they only need to hash it once to see whether it produces a correct hash. They'll check all of the information inside the block too, whether it was built on a previous block and whether the transactions are authentic. This dynamic, expensive to produce, cheap to verify, is some of the game theory that makes blockchain systems viable. You'll be out of pocket if you produce an invalid block, as the other nodes will immediately reject it. Proof of work was the first consensus mechanism to surface and remains important. This process of using proof of work to solve a block is called mining, and nodes that participate in mining are called miners. We call them miners because they're working to extract a reward from the protocol. Despite proof of work's strength for preventing system abuses with a high level of security, it has some limitations. For one thing, when the network becomes larger, it requires expensive equipment and high energy usage. Therefore, alternative consensus mechanisms were introduced to mitigate these limitations. A prominent alternative consensus mechanism is called proof of stake, which was proposed back in 2011. Proof of stake mechanisms use a pseudo-random election process to select validators from a group of nodes. The validators hold and stake the native cryptocurrency of the blockchain in order to validate transactions. Staking refers to the act of validators committing funds to the blockchain network. The locked funds will then act as collateral, meaning malicious validators will most likely lose their stake and be kicked out. On the other hand, honest validators will be rewarded as new blocks are produced. Generally, the more coins are staked, the more likely you get to validate a new block and receive rewards. Beside proof of work and proof of stake, there are other alternative consensus mechanisms. Delegated proof of stake and hybrid POW/POS are two examples. To sum up, consensus mechanisms are critical to allow distributed systems to work together and stay secure, and proof of work and proof of stake are two dominant mechanisms. In this module, we'll discuss the different kinds of nodes, blockchain network structure, and how conflicts are resolved in a permissionless setting. In blockchain systems, not all nodes are the same. Under the broadest definitions, any machine that interacts with the network in some way can be considered a node. So far, when we've talked about nodes, we've been discussing full nodes, nodes that have a full copy of all the blockchain's transactions. When a full node receives a block, it will perform checks on the contents of the block, including the timestamp, hash, and difficulty. Amongst other things, it must verify each of the transactions on whether the inputs have previously been spent, whether the signature matches the public key, whether the sum of the inputs is greater than or equal to the sum of the outputs. If it's satisfied, the node will keep a copy of the block and propagate it to the rest of its peers. A full node is the best way to get an accurate image of the blockchain. Without one, you need to trust a third party to feed you the data you need. But because they download, validate, and store all of that information, they might not appeal to everyone. The Bitcoin blockchain is over 400 gigabytes as of mid-2022. Nodes download and validate blocks at 10-minute intervals. To some, this may be a strain on storage and bandwidth. On the other hand, light nodes are devices that connect to other nodes, but perform limited validation on the data. Because of this, they have lower storage and bandwidth requirements, and can be run on devices such as cell phones or low-end computers. If you use a non-custodial wallet, that's most likely a light node. Instead of downloading full blocks, light nodes download only the block headers, which are much smaller in size. The block header gives you important information such as previous block hash, timestamp, and other metadata. Ultimately, light nodes rely on full nodes to operate. Then, there are mining nodes. Technically, mining nodes are either full nodes or light nodes, but these are a subset of nodes that perform the proof of work necessary to secure the network. For cryptocurrencies like Bitcoin that use proof of work consensus mechanisms, a simple computer isn't enough to perform the hashing operations. Because there's so much competition in mining, specialized machines must be used. Examples include GPUs, as you might find in gaming computers, or purpose-built devices like application-specific integrated circuits. We say that public blockchains are permissionless and anyone can become a node. You might be wondering, with nobody in charge, how can changes be made to the network? In a truly decentralized network, changes can be made with soft forks or hard forks. A hard fork occurs when you want to introduce changes to the software that make older nodes obsolete. The network is effectively fragmented into two parts, one made up of old nodes and one made up of upgraded nodes. The two can't communicate. For all intents and purposes, there are now two networks. Soft forks are upgrades to the network that are backward compatible. Certain upgrades can be added in a way that doesn't interfere with the regular functioning of the network. For instance, a block size reduction. A soft fork might be preferential in scenarios where you don't want to divide users into different camps. In effect, the upgrade is considered opt-in. Certain newer features might be invisible to you, but you can still communicate with the upgraded nodes. Whew, that's a lot we've covered in the first 5 modules. In the next and last module of this course, we'll go over blockchain use cases and its limitations. Now, we have a general idea of what a blockchain is and how it works, but what can it actually be used for? Let's review some of the important fields where blockchain technology is being utilized. Sending money between different parts of the world can be quite expensive, with middlemen charging hefty fees for what's essentially moving bits around on the internet. How would you react if it suddenly took 3 working days to send an email? While sending money is a more delicate matter than sending an email, the remittance infrastructure is undoubtedly outdated. Sending money via blockchain can be fast and incur low fees. Many countries have or are considering issuing central bank digital currency, also known as CBDC. It's the digital form of a country's fiat currency. This could have a huge impact on the remittance market and the global financial services market. You've probably also heard about blockchain's use cases in the decentralized finance space. The idea of DeFi is to create a more open, inclusive, decentralized, and transparent financial system that runs on top of public blockchain systems. By removing financial intermediaries, DeFi gives people direct control of their assets and permits them to conduct peer-to-peer transactions. Moreover, blockchain technology is quite reliable in storing records with high data integrity, while enabling many different participants to use the same database as a shared source of truth. Supply chains involve many different companies that have to integrate their systems with each other to handle goods from suppliers to consumers, often across borders and through customs. Blockchain technology can make interactions between businesses smoother and more efficient, which ultimately benefits the economy and the consumer. Similarly, storing digital health records is essential for an efficient healthcare system. This delicate data has to be stored and shared with exceptionally high security standards. Blockchain technology can make digital health records more secure and private. Blockchain has many other use cases in industries such as gaming, charity, and energy. It also provides an alternative governance mechanism for organizations. But ultimately, it's still a developing ecosystem, and more transformative applications may be uncovered in the future. Blockchain technology does have some limitations, however. Blockchain's immutability comes with a downside when it's necessary to make changes. There aren't many good solutions to this problem, and this can hinder the evolution of a blockchain system. Blockchains use public key cryptography to secure the ownership of value in the system. If a user loses their keys, the value that those keys grant access to becomes inaccessible forever. Blockchains, and more specifically, Bitcoin, has been a target of criticism over its high energy consumption. Another limitation to consider is storage. As the size of the blockchain grows, the entry barrier could become higher. What follows is that there would be fewer machines in the distributed system, which may have a detrimental effect. The network's resilience to attacks and exploits could dwindle. Speaking of attacks, one of the most discussed is the 51% attack. If malicious actors could amass more than 50% of the mining power, the attackers would be able to undermine some of the fundamental workings of the blockchain. In reality, though, such an attack would be incredibly costly and difficult to pull off. Well, that's a lot we've learned in this Blockchain Fundamentals course. Congratulations for completing this course. Remember to check out Binance Academy's website and follow us on YouTube, Facebook, and Twitter to stay tuned for future courses. See you in Binance Academy's next course.